that the bonding states are going to be lower in energy than the anti-bonding states. So we usually show these relative energetics in diagrams like this. So what I've here for reference is the energy level of a unmodified atomic 1s electron, specifically in hydrogen. So they're at this level energy right here. And the rule is that the bonding molecular state, molecular orbital, is going to be lower in energy than the atomic orbitals that you sort of constructed it with. And the anti-bonding configuration, so what does that look like? Well, it looks a bit like this. Broadly speaking, you can just see that this is just, a 1s plus a 1s, and you get, so if you imagine putting two spheres on each other, you would get something that looks like this. The anti-bonding configurations tend to be higher in energy, not tend to, they are higher in energy than the atomic electron states from which they are constructed. So we got this, and note that this is not symmetric, and this is a thing. The anti-bonding states are more anti-bonding than the bonding states are bonding. But I have greatly exaggerated the difference here. If it were true to scale on this particular graphic, you would hardly notice the difference at all. So what does that state look like? Well, so let's talk about how to draw these, shall we? So this configuration is basically going to be a 1s from hydrogen A minus the 1s from hydrogen B. And so basically all you need to know is the relative shapes of these orbitals, and if one part is negative, one part is positive, and what's overlapping. And it's pretty simple. So this one, so what you do is, so we've got a 1s state here, and let's say that this one we're going to call, so s electrons don't change sign, the wave functions don't change signs, so they're all one sign, we'll call it the red sign. But you're subtracting, so you're adding the negative, so this other one is going to be the opposite sign, and throughout this graphic I've got them, the two signs shown as being just red and blue. Now the way you just approximate what that orbital looks like is draw them such that they actually overlap a little bit, not completely, but just at the outer edges. So this is going to end up being something like this, except imagine them being the same size. And the rule is that if areas of the opposite sign overlap, which is the case here, they will cancel each other out. So basically what you want to do is almost erase the overlapped area and then close up what's left. So you would have the red area border would be there, and the blue area border would be here. And I don't think the eraser is going to let me do this in the PowerPoint, so I'm just going to draw it new here. So the result is you're going to have a red part that looks something like this. The blue part is going to look something like this. But you don't want this thing. I'll try this again. And again, for reference, the nuclei would be like right here. So, and the other thing to note is that we do have a node in here. All right. I'll do a few more examples like that. Now, how did we get this one, the lower state? Well, we've got two areas of the same size, same sign, and the rule there is that if they overlap, you actually just kind of meld them together. So in this case, what you want to do is join them where that overlap is. So this becomes, and that's how we get sort of this round shape here, and the nuclei are about right here, where the H's are here. So the other state looks a little like that. And let me just get rid of all this stuff so you can see. So you can see where this comes from. What I do want to do here is kind of show again the node in between the two. So this is an energy level diagram. We've got two states mapped out here. So we combine two atomic states, these guys, and remember, these are here just for reference. But these are the states that are sort of at play now. We occupy them just like we did the atomic states, and the rule is that you can have 2 electrons in any one of these boxes in any one of these states. Now, hydrogen has 2 electrons. So they would both go in this lowest state. Remember, you start from the lower energy states, work your way up. And from this, we can actually construct the bond order, or the electron configuration of H2. And now let's look at this. This is called a sigma, so this is the same terminology that we looked at some of the valence bond things. If you look down the bond axis, you basically just see a circle. So this is called a sigma type molecular orbital. This one you would kind of see a circle too. That it would, it would be, you would not see a node going out radially anywhere here. And the star indicates that it's an anti-bonding state, and the lack of star here indicates that this one is a bonding state. And you construct electron configurations just like we did with atoms. So you just write down the label for that particular state, and then with a superscript, tell me how many electrons have that or in that state. And usually we use parentheses just to kind of keep things a little manageable. So this electron configuration would simply be 1s squared. Right. Now, so the anti-bonding orbital or the anti-bonding state here doesn't really matter much because no electrons have that state. The 2 electrons that are in your average H2 molecule are both in the bonding state, hence H2 molecule is a thing and it exists. So the other thing that we need to understand is this thing called bond order. All bond order is tells you relatively how many more bonding electrons do you have than anti-bonding electrons. So bonding electrons help the molecule stick together. Anti-bonding ones would encourage it to fly apart. As long as you have more bonding electrons than you do anti-bonding electrons, you're fine. So the formula, specifically speaking, is that you take the number of bonding electrons minus the number of anti-bonding electrons, and then simply divide it by 1/2. And the reason this is there is simply because, we talked about bonding before as a shared pair of electrons. So that factor of 1/2 is there to kind of align these answers with the original Lewis theory, such that a pair of bonding electrons sort of counts as a bond. And in this particular case, let me erase my artwork here. So we've got 2 bonding electrons, we have 0 anti-bonding electrons, so the bond order is said to be 1, which is analogous to a single bond. All right. So let's move on with this. Let's add one more electron to the mix and talk about OH2-. So H2- has 3 electrons in it. All right, so let's populate those. So as we did before, we can put 2 electrons in that bonding state, but that's all you can do. So now we need to add that last electron in the anti-bonding state. And there we go. So the electron configuration here would be sigma 1s2 and sigma 1s star 1. Bond order. So now we've got 2 bonding electrons, 1 anti-bonding electron. That gives us a bond order of a half. So a half bond. This is something that Lewis structure didn't like in molecular orbital theory. It's fine. The important thing to note is that the greater the bond order, the stronger that bond and the shorter it is. So H2-, while it's still stable because the bond order is greater than 0, that bond is not as strong as it is in H2, so it's not the happiest of campers, but it is an actual thing. All right, so let's do one more. All right, helium. Now the nice thing is, so even though the wave function for a 1s wave function in helium isn't exactly the same as the function in hydrogen, the form is exactly the same. And the end result, at least the overall broadly speaking, the molecular orbital energy level diagram is going to be exactly the same. The numbers, like this exact energy and this exact energy, would be different, but as far as what the picture qualitatively looks like, exactly the same thing, which is very useful. Now let's consider He2. Now how many electrons does this guy have, or how many valence electrons? So 4, and they're all valence electrons. So we put 2 in the in the lowest, or the bonding state. The remaining 2 go in the anti-bonding state. So the electron configuration for He2 would be sigma 1s2, sigma star 1s2. Now the bond order, we have 2 bonding electrons, we have 2 anti-bonding electrons, and this gives us a bond order of 0. So what does that mean? Does that mean that the thing is a neutral or there's no overall bonding? No, it does not. Now remember that this energy was higher. This energy was pushed up more than this energy was reduced. So a bond order of 0 actually means that there's not a bond at all, that this molecule would actually fly apart. Now helium is a noble gas. We keep telling you that they don't do much. This would be an example of that. And normally at this point, the instructor would tell you, and that's why there's no such thing as He2. And when I was a graduate assistant at Michigan State, I was a TA for their version of this class, and the instructor said just that. And then I had to raise my hand and say, excuse me, turns out that is not the case, because earlier that week, this paper had been published, and someone actually had created at a fraction of a degree above absolute 0 He2. It's an incredibly weak bond, and these guys are at the University of Minnesota. And it turns out that there are other ways that atoms can associate with each other than electron pair sharing or just electron sharing. This is an example of that. But it was kind of fun to be able to contradict the instructor right there in front of the entire class of about 300 people. And I will say to his credit, he adjusted his notes and always talked about this, and I do too. As another aside, this was funded by the National Science Foundation, so everything about it is publicly known. This was a complete accident. This was not what they were proposing to do with this money. It seemed like they just accidentally observed it while they were doing their actual experiment, but caught it, wrote it up. and now they're the subject of many Gen Chem side points. All right, so that's it for the very intro for molecular orbital. So the next video, we're going to talk about how to combine more complicated functions. All right, we'll see you there.